Assalamu alaikum everyone, and welcome back. Today we are going to cover lecture 23, and this is week 12. We are starting chapter 10, and chapter 10 is about capacitors. So in up till now we were considering and using resistors in our circuits, and now the second important element that is used in circuits is called the capacitor. Another element which is frequently used is inductor, that we will cover in next classes. So what is capacitor? We are going to introduce it in this class, and how this capacitor is formed, and what is its applications that we will see during the lecture. So this is your textbook, Introductory Circuit Analysis. Today's lesson contents are introduction to the capacitor, electric field, what is capacitance, dielectric strength of a capacitor, and leakage current in the capacitor, and stray capacitance. So unlike the resistor, capacitors and inductors display their total characteristics only when a change in voltage or current is made in the circuit in which they exist. That is, in the resistor, the value of the current is directly proportional to the voltage. If voltage is increasing, the current would also increase, and vice versa. For a particular value of the voltage, if voltage is a constant voltage is applied, the current would be constant. But if in capacitors and resistors, if a constant voltage is applied across these elements, then there would not be any current in these components. The current would only flow when there is a change in the voltage occurs across these components. So if we consider the ideal situation, they do not dissipate energy as does the resistor. So these two components does not dissipate the energy, unlike resistor. A resistor is an energy dissipating element. We have seen that power dissipation occurs in the resistor when the current flows into the resistor. But in capacitors and inductors, they actually store the energy. So they store the energy is stored in a form that can be returned to the circuit whenever required by the circuit design. So capacitors and inductors are energy storage elements. So first of all, what is the capacitance? So for that, consider two parallel plates which are uncharged or neutral. These two parallel plates, initially they are neutral, that is, there no charge exists, and they are made of conducting material separated by an air gap, have been connected through a switch and a resistor, and to a battery. So the capacitor is constructed with parallel plates usually, and we are considering two parallel plates which form a capacitor, and initially these plates are neutral, and when they are connected with a battery through this resistor and a switch, then what happens is the instant the switch is closed, electrons are drawn from the upper plate of the battery through the resistor, to the positive terminal of the battery. That is uh, the when this switch is closed, what happens is this path is completed, and there is a chance for the electrons which are free in the upper plate of the capacitor. We know that this is a conducting material, and for any material which is a conductor, and conductor have free free electrons present within the conductor, and when we connect a battery with this conductor, these free electrons are attracted by the positive terminal of the battery, as positive and negative attract each other. So there will be a surge of current until the potential difference across the parallel plates is exactly equal to the battery voltage. So this current would keep on flowing in this path until the battery voltage and the voltage across the capacitor becomes equal. So this voltage is equal to this voltage, and at the moment when these two voltages become equal, then current in this resistor becomes zero. That is, the potential difference across the resistor becomes zero, and the current becomes zero, and no further charge would be accumulated on these plates. The final result is a net positive charge on the top plate and a net negative charge on the bottom plate. So जितना जो पॉजिटिव प्लेट के ऊपर चार्ज एक्युमुलेट होगा, उतना ही नेगेटिव प्लेट के ऊपर चार्ज एक्युमुलेट होगा. पॉजिटिव प्लेट के ऊपर जो चार्ज होगा दैट वुड बी पॉजिटिव, and there is an equal amount of negative charge that is accumulated on the negative plate. So this situation is very similar to the one in which there are two isolated positive and negative charges in a certain field. The element formed by two parallel conducting plates separated by an insulating material, in this case it is air, is called a capacitor. So these two plates are not touching each other, there is a gap between these two plates. These two plates are not touching each other, rather there is a air gap between these two plates, and when this capacitor is charged, that is, the plate has a positive charge and this plate has negative charge, and if battery is removed, that is, switch is opened, then this charge would stay on these two plates, and there would not be any current that would flow between these two plates, and this becomes a source of potential. So capacitance is a measure of capacitor's ability to store charge on its plates. In other words, it's storage capacity. So capacitance is a measure of ability to store a charge. So higher the capacity to store a charge, higher would be the capacitance. For example, if you have two so for example, अगर आपके पास let's say दो glasses हैं, एक जो glass है वो उसका size बड़ा है, so for example if you have two buckets of water. One is bigger than the other. The bucket which is bigger one has more capacity to store the water as compared to the one which is smaller. So similar to the capacitor, the larger the capacitor, more it can store the charge on its plates. So this is the capacitance is the ability to store the charge. A capacitor has a capacitance of 1 farad if a 1 coulomb of charge is deposited on the plates by a potential difference of 1 volts across the plates. The farad is named after Michael Faraday, 19th century English chemist and physicist. The farad, however, is a generally too large measure of capacitance for most practical applications, so microfarad or picofarad is more commonly used. A minor analogy is that of a resistance which is measured in ohms. Is the capacitance measured in farads. But note it is not resistance, rather a storage capacity. So capacitance is determined by this equation, which is capacitance is equal to charge per unit voltage, that is how much charge is accumulated for a given voltage, that is determined by the capacitance. So higher the charge stored in the capacitor, higher would be the capacitance. Next is a cross-sectional view of a parallel plate is shown with uniform distribution of electric flux lines. So this is the electric field that is established between the positive and the negative plates. Whenever there is a positive and negative charge, electric field force lines are established between those charges. Same is the case for a capacitor, as capacitor has these plates having charge on each plate, so as a result there would be an electric field between these plates. At the edges, the flux lines extend outside the common surface area of the plates, producing an effect known as fringing. So you know that the electric field is also going out for any charge, positive charge or negative charge. Electric field lines come out in different directions. So here as well there is an electric field that would be distributed in the edges as well, but more field would be within these plates, and there would be a very small percentage of electric field that is established at the edges, and this effect is known as fringing. This effect reduces the capacitance somewhat, but can be neglected for most practical applications. So for the analysis, we assume that all the flux lines leaving the positive plate pass directly to the negative plate within the common surface area of the plates. So we ignore the fringing effects and only consider the flux which is established within the plates. Now if a potential difference of V volts is applied across the plates, if there is a potential difference of V volts here, and these plates are separated by a distance d, this is the distance d, this is d, The electric field strength between these plates would be equal to E. So what is the electric field between these plates would be equal to V by D, where V is the voltage between these plates and D is the separation between plates. So mod is the voltage across these plates, more would be the electric field, and if D is smaller is the separation between the plates, higher would be the electric field. Sorry, the smaller the distance between plates, the higher would be the electric field. Many values of capacitance can be obtained for the same set of parallel plates by the addition of certain insulating material between the plates. So at start we consider that the region between the plates is a free space, that is air, and so initially we consider that there is a free space or air between these two plates, and the capacitance of the capacitor is determined. But if we insert some material within these two plates, which should be an insulator, because we would like that there should not be any charge that could flow from one plate to the other. So the material that should be inserted between these two plates should be an insulator. So if we insert some kind of insulator within these plates, then this would affect the capacitance of the capacitor, that we will see shortly, that how this medium will affect the capacitance of these two parallel plates. So many values of capacitance can be obtained for this same set of parallel plates by the addition of certain insulating material between the plates. So in figure A, this is the figure A, in an insulating material has been placed between a set of parallel plates having a potential difference of V volts. So again a V volts is applied between these two plates, and these two plates are having certain capacitance, and a medium is inserted between these two plates. So initially when there is no charge on the capacitor, then this would be the scenario of the insulating material, that is within the insulating material the atoms of of the insulator would have these kind of orientations, in which you can see for any atom you have a proton and an electron revolving around this. Now since the material is an insulator, the electrons within the insulator are unable to leave the parent atom and travel in the positive plate. So what happens is, however, force of attraction and repulsion of the positive repulsion from the plates causes a shift of protons and electrons within each atom, thus creating dipoles within the insulating material. That is, within the insulating material there are electrons and protons. There are atoms, and for every atom there is a proton and an electron, and these atoms are randomly aligned in the absence of any external electric field. But when we apply a electric field across the insulator, then what happens is, within the insulator the atoms of the insulator are aligned in such a way that the electrons are attracted by the positive plate, and protons are attracted by the negative plates, and they start aligning. This would move clockwise and stay upward, so that the negative uh, charge is attracted with positive charge of the upper plate, and the protons is attracted towards the negative plate. So you can see that all these protons are aligned, are towards the negative plate, and all these electrons are aligned towards the positive plate. So this would be the scenario that electrons would try to negative charge would try to align with the positive plate, and positive charge would try to align with the negative plate. This phenomena is called dipole. Dipole has two poles. Di is per 2, that is it has two poles, one is positive and one is negative, and dipole has many applications in electrical engineering. When the dipoles align themselves, the material is polarized. So the positive and negative components of adjoining dipoles neutralize the effects of each other, except the layer of positive and negative charges near the plates. What it means that you can see that this positive and this negative, this layer and this positive layer and this negative layer, they neutralized each other. Similarly, this positive layer is neutralized with this negative layer. However, this layer of positive charge would not be neutralized by any negative charge layer. Similarly, the outer layer, this one, would not be neutralized. So within the insulator, there would be a net negative charge on one side, and there would be a net positive charge on the other side, so resulting in the establishment of an electric field, that is E dielectric, within the insulator, as shown in the next slide. So this is the electric field that is established between positive and negative charges, and this is the electric field that is established due to the capacitor plates. Sorry, this is the electric field that is established due to these parallel plates, and this one is the resultant net electric field. One electric field is from left to right, and the other electric field is from right to left. So net field would be the sum of these two. The resultant electric field would be the difference between these two electric fields. So the net field would be the electric field of the capacitor without the dielectric, that is only with air, and minus the electric field due to the dielectric. So this net electric field between the plates would therefore be reduced due to the insertion of the dipole. So what would be the effect of the dielectric or insulator within the plates is that the net electric field would be reduced, because net electric field is the difference of the electric field between air and the dielectric. Now, due to the opposing effect of net electric field, the resulting material is referred to as dielectric, di for opposing and electric for electric field. So this due to this effect, this material, insulating material, is called dielectric because it opposes the electric field. So this electric field is given by this. We have seen the relation. Next is the permittivity of the dielectric. What is the permittivity? In electromagnetism, the absolute permittivity, often simply called permittivity, and it is denoted by the Greek letter epsilon, is a measure of the electric polarizability of dielectric. So we have seen that the insulator within the electric field is polarized, and dipoles are created within the insulator. So the ability of a material to get electrically polarized is called the permittivity of the material. So what is the permittivity? It is a measure of the electric polarizability of dielectric. So a material with high permittivity polarizes more in response to an electric field than a material with low permittivity, thereby storing more energy in the electric field. सो अगर जो आपकी जो परमिटिविटी ज़्यादा होगी, इसका मतलब यह है कि आपका जो मटेरियल होगा वो ज़्यादा पोलराइज होगा, और उसकी वजह से जो नेट इलेक्ट्रिक फील्ड होगी वो ज़्यादा डिक्रीज़ करेगी. सो नेट इलेक्ट्रिक फील्ड जब डिक्रीज़ करेगी तो वी विल सी दैट इट विल इंक्रीज द कैपेसिटेंस. So we will see relationship between electric field and capacitance in a short time. In electrostatics, the permittivity plays an important role in determining the capacitance of a capacitor. So this is the permittivity of the dielectric that is inserted between the plates, and its value would determine the capacitance of a capacitor. So if we insert a material within the capacitor plates, then the value of the capacitance would be changed. It would either increase or decrease depending upon the permittivity of the material inserted. For a vacuum, epsilon denoted by epsilon naught, this is for reference, and its value is 8.85 into 10 to minus 12 force per meter. The ratio of the permittivity of any dielectric to that of a vacuum is called the relative permittivity, and is denoted by epsilon r, and it is defined as epsilon r is equal to epsilon divided by epsilon naught, where epsilon is the permittivity of any dielectric, and the ratio of this permittivity of any material to the permittivity of free space is called the relative permeability of the material. So the relative permittivity epsilon r is a dielectric constant and a dimensionless quantity. It simply compares the permittivity of the dielectric to that of the air. So if we know the relative permeability of a material, we can find the permittivity of that material by this relationship, that is epsilon is equal to epsilon r into epsilon naught. So how much the relative permeability of a material corresponding to the permittivity of the free space will determine the value of the permittivity of that material. So in this table we are given with the average values of the relative permittivity of dielectric material for various dielectrics. So there are dielectric materials, different dielectric materials, and the corresponding relative permittivity of the material corresponding to the free space, that is vacuum. So for vacuum the relative permeability is 1, and for air it is also close to 1, but for other materials, that is, let's say for Teflon, its relative permeability is 2, that is its permittivity would be 2 times the permittivity of vacuum. Similarly for let's say mica has relative permeability of 5, that is its permittivity would be 5 times higher than the permittivity of free space. Next is how we calculate the capacitance of a parallel plate capacitor. So for a given parallel plates, if we want to calculate the capacitance, then the value of the capacitance would be equal to epsilon naught epsilon r into A over D, where A is the area of the plates and D is the separation between the plates. This equation is derived through these steps, and we know from the feed between the plates is given by this equation E. Where this equation is derived through these steps, the electric field between the plates is given by this relationship, that is E is equal to Q over A into epsilon, where A is the area of the plates and epsilon is the permittivity of the material. And we can come to this relationship through these steps. That is from Gauss's law. The flux is determined by charge per unit epsilon. That is from Gauss's law. Phi is equal to Q enclosed divided by epsilon, but Q enclosed is equal to sigma into A, so phi would be equal to sigma into A over E. But the charge is equal to sigma into A. The charge of a plate is given by charge density into the area, so flux would be equal to charge per unit epsilon, and flux is also equal to E into A. That is the flux is the field number of field lines that is determined by the electric field, and that flux passing through certain area would be equal to E into A. So therefore this E into A would be equal to Q over epsilon, and from here E can be determined by Q over A into epsilon. So this is the electric field between the plates, but we have seen that E is also given by V by D, so V by D would be equal to Q over A into E. So from here we can rearrange this relationship for epsilon. So epsilon is equal to Q D over VA, and similarly we know that C is equal to Q over V, and thus epsilon would be equal to this Q over V is replaced with C into D over A. So from here C can be determined as epsilon into A over D, and the value of epsilon can also be written as epsilon naught into epsilon R. So this is the relationship to determine the capacitance of a parallel plate having some dielectric is inserted into the plates. So for example, this is for this is the relationship, and epsilon naught, value of epsilon naught is given, and this is epsilon r. So for any material uh, that we have seen in the table, if having a relative permeability is inserted, that will determine the value of capacitance for a given capacitor dimensions with area and separation. So where A is the area in square meters of the plates, D is the distance between plates in meters, and epsilon r is the relative permittivity. So the capacitance therefore will be greater if the area of the plate is increased, or the distance between the plates is decreased, or the dielectric is changed so that epsilon r is increased. So if epsilon r increases and area increases, capacitor will increase. If D is decreased, capacitance will increase. So let me see an example. Determine the capacitance of each capacitor on the right side of this figure. So this is the parallel plate capacitor whose capacitance is required to be determined. So on the left hand side, a capacitor is given whose value is 0.1 microfarad, and the separation between the plates is D, and if we increase the separation between the plates, that is we double the separation, then what would be the capacitance? So this is the similar capacitor with the same area and same dielectric, but the separation is increased by 2. So what would be the capacitance? As you know, if separation is increased, the capacitance will decrease. So if separation is increased 2 times, the capacitance will decrease by half. So net capacitance would be 0.05 microfarads. Next example is determine the capacitance of a capacitor on the right side of this figure. That is, this is the capacitor whose capacitance is required to be determined, and on the left side, capacitor whose value is given as 1000 picofarads and having area A and separation D, and the dielectric is air, that is no medium is inserted between the plates. No dielectric is inserted between the plates. So if we increase the area, this area is increased 4 times, and the separation between plates is decreased by 8 times, and a material is inserted between these plates, and the material is mica having relative permeability of 5. Then what would be the capacitance with these new parameters? So we can see that from the relationship that if area is increased, the capacitance will increase. So 4 times area is increased, the capacitance will increase 4 times. The separation is decreased 8 times, so capacitance will increase 8 times. The dielectric is inserted, so value of epsilon r is increased 5 times, so capacitance would also increase 5 times. So this capacitance of 1000 microfarad would increase 4 times due to 4 times increase in area and 5 times increase in the material, and 8 times increase in this separation, because diameter is reduced by 8 times. So net effect would be this 8 would bring into the numerator. So 5 into 420 into 8, 160. 160 times capacitance will increase. So new value will be 0.16 microfarad. And next example is for the capacitor of figure having 450 volt across plates. Determine the electric field strength between the plates with and without a sheet of mica between plates. So in this example you are given with the voltage across the capacitor for 50 volts, and you are asked to find out the electric field strength, that is E. So E is given by V by D, and D is the separation, is given as 1.5 millimeter. So converting into meter by multiplying it with 10 to the minus 3. So so E would become equal to 450 divided by 1.5 into 10 to the minus 3 meter, which is approximately 300 into 10 to the power 3 volt per meter. So this electric field would not be affected by the material inserted. The value would stay approximately the same. Next is the example in which capacitor of figure having 450 volts across plates, find the capacitance with and without a sheet of mica between plates. So the same capacitor, you are asked to find out capacitance. So first of all, for air between the plates, C naught would be equal to epsilon naught A over D. A is given as 0.01 meter square. Epsilon naught value is given, it is constant, and D is the separation. So by plugging the value, C naught would be equal to 59 picofarad. Now with the mica inserted between the plates, what would be the value of capacitance? For mica you have relative permeability of 5, so capacitance would be 5 times this value, so it is 295 picofarad. So next example is find for the capacitor of figure having 450 volts. So this is the same capacitor. Now you are asked to find the charge on each plate with and without mica. So first of all, without mica, that is with air between plates, Q would be equal to we know that Q is equal to C into V. C is the capacitance we have already found in the previous slide. It is 59 picofarad and voltage is given, so charge would be 26.55 nanocoulomb. Now if we insert the mica between the plates, then what would be the charge? So intuitively you can say that the charge would be 5 times higher than this value. However, we can compute it from this relationship, so we will end up with the result that 5 times the amount of air between the plates. This value would be 5 times this value. Next is dielectric strength. For every dielectric, if potential difference exceeds certain limits, it will break the bonds within the dielectric and cause current to flow. So we have inserted an insulator between the plates, and we would like that no current flow from one plate to the other, but if the insulator breaks down, then there would be a current that would flow between the plates, and the insulator would break down at a certain potential, and that property of the material is determined by its dielectric strength. So the voltage required per unit length to establish condition in a dielectric is an indication of its dielectric strength and is called the breakdown voltage. So a typical example of breakdown is lightning between clouds and earth with air as its dielectric. So this table will show the dielectric strength of some dielectric materials, and it is given in volts per mil. So for air it is 75 volts per mil, and so let's see an example. Find the maximum voltage that can be applied across a 0.2 microfarad capacitor having a plate area of 0.3 meter square. The dielectric is Brockland, having a dielectric strength given by this number 200 volt per meter. So we would like to find the maximum voltage that can be applied for this capacitor having dielectric as Brockland, and its dielectric strength is 200 volt per meter, and this is the dimension of the capacitor plates. So with the given dimension of the capacitor plates, how much voltage we can apply until this dielectric would break down. So from the relationship of capacitance, we have capacitance given by this equation, from which we can find out the value of D, that is separation between the plates. The other parameters are known to us, so D is computed to be 79.65 micrometer. So converting the micrometer into mils, we have 3.136 mils against this value, and dielectric strength is given to us as 200 volt per mil, and from which we can find out the value of voltage for this much mils. So for 1 mil it is 200 volt, for this much mils it would be 627.20 volts. So if for this separation between the plates electric field would be strong enough, if voltage of this much volt is applied between these plates having this much separation, or this much separation in mils, with the 200 volt per mil separation, if separation is 1 mil, then we can only apply 200 volt, but if we have this much separation between plates, the voltage that we can apply is now a bit higher than this value, and it would be 627.20 volts until the dielectric would break down. Next is the leakage current. So far we have assumed that the flow of electrons will occur in our dielectric only when the breakdown voltage is reached, and this is the ideal case. That is when the dielectric within the plates is not into the breakdown and working properly, then it would not allow any current from one plate to the other. So this would be the ideal case, but practically due to some impurities within the dielectric material, small leakage current would flow from one plate to the other because of the tendency of the voltage of one plate with respect to the other, it would like to support the current through this gap, and if there is a possibility for any current, then this current would be flowing through these plates, and this current is called the leakage current. So in actual case, there are free electrons in every dielectric due to part 2 impurities in the dielectric and forces within the material itself. So that current is called the leakage current. So when a voltage is applied across the plates of a capacitor, a leakage current due to the free electrons flows from one plate to the other. So the current is usually negligible. This effect is represented by a resistor in parallel with a capacitor as shown in this figure, whose value is typically very large and typically above 100 megaohms. So some capacitors, however, such as the electrolytic type, have high leakage currents. So when charged and then disconnected from the charging circuit, these electrolytic capacitors lose their charge in a matter of seconds because of the flow of charge, that is leakage current, from one plate to the other. Next is the stray capacitance. Stray capacitances exist not through a design but simply because two conducting surfaces are relatively close to each other. So when we have connecting wires or conductors that run parallel to each other, there would always be a capacitance that would be created within these conductors. These capacitors are not intentionally created, but they are part and parcel of an electric circuit in which two conductors are running in parallel. So two conducting wires in the same network will have a capacitor effect between them as shown in figure A. Similarly, these stray capacitances are also created between the junctions of a transistor. Between each junction there is a capacitance. Between these two junctions there is a capacitance. Between this junction and this junction there is a capacitance created. So these stray capacitors can often lead to serious errors in system design if they are not considered carefully. So this is the summary that we have covered today with introduction, electric field, capacitance, dielectric strength, leakage current and stray capacitance. So thanks for today. Allah Hafiz.